they
Okay.
always usually ask the graph or
Hey. Oh yeah. I think I'm not 100% sure, but I think every exam has at least one graph question. But I'm not 100% confident, but every exam I've looked at, they have it. Yeah, so I think they should, yeah. They should have a graph question. All right, let's look at this one now. Let me get this actually a little bit bigger. Right, so A part 1 now. What's this difference between longitudinal and progressive transverse waves? So in other words, what's the difference between longitudinal and transverse waves? Which one?
Longitudinal.
Yeah. And transverse? You've just done the same thing twice.
No. I did this.
Which one's that?
Longitudinal is.
Yeah, okay. And then transverse? Yes, very good. So the longitudinal one is like this one.
Let me explain it by John.
No, that's just helping me to draw it. Focus here, focus. So you can say here is the direction of the wave. So the key word here is that the wave propagates, well, I think I'll use an easier word, travels. I should actually say the wave energy maybe if you want. Travels in the same direction as motion, I don't know. So the wave travels, no, that sounds stupid. Don't write that down, that's stupid. Yeah, we should use the word source. I'll go with wave energy moves out from the source in the same direction as the wave. Now the other one, what's wrong? It's not the same. The transverse one looks like this. Oh, sorry. The transverse one looks like this. Oh man, you get the idea. Transverse, close enough. So in this one, the energy is going up and down. So it's going in a perpendicular. So I won't even bother to write it again. Blah, blah, blah. But instead of the same direction, it's in a perpendicular direction. Yeah, blah, 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 perpendicular. Don't write that in the exam. Don't. Okay. You have your light. Snell's law. Now, your light goes in with this speed. Oh, sorry. Which type can be polarized?
Polarized.
Long or transverse?
No, not transverse.
No. Sorry. Long. Yeah, polarized is when you make the wave look like this. So it can't be this to begin with. So it's the other one.
What's polarized mean?
Polarized actually means to change it into a transverse wave. Polarized means to change it into this wave. To change it into a transverse wave. So what do you begin with? You must begin with a longitudinal wave. Because it doesn't make sense to change a transverse wave into a transverse wave, you know? And an example would be light. Yeah. So actually, hang on. The answer is longitudinal. Okay. Now we have our light with this speed inside a block of glass towards its boundary with air. Determine the refractive index with glass. So this is the speed inside the glass. Okay? So if you look here, if you want to draw the picture of it, air and glass basically. So the light comes in, at some angle I, and then refracts out here at angle R. And we know the speed roughly. What's the speed of light in air? Yeah, roughly c. That's actually in a vacuum, but no big deal. And glass, he gives it to us. What is it? 2 times 10 to the 8. And what's he asking for? Oh, okay, so I don't actually have to do this IR stuff yet. Okay, so refractive index, it is, what did we say? The velocity, yeah. Which way around? Hang on. Let's think about this for a moment. When we did our Snell's law experiment, what answer did you get? Was 1 point something, wasn't it? Yeah. So it should be a number more than 1, not less than 1. So the bigger one has to always go on the top then. So that's C over V then. That's what it is, yeah. So the formula is C over V. So here, 3, isn't it? Times 10 to the 8. Oh, well, this is easy. 2 times 10 to the 8. So it's just 2 over, oh, sorry, 1.5, thank you. Is that okay? Yeah? That's actually easy. What's next? Determine the minimum angle of incidence at the boundary for total internal reflection to occur. Now, in this story here, it starts inside the glass and goes out to the air. So, in fact, this here is air to glass, but really what it is this one here. It's in the glass, and it's trying to get out to the air. And there's some angle. Isn't that what he wants? Determine the minimum angle of incidence at the boundary for total internal reflection to occur. Okay. So let's just think of some examples logically. If it's coming in at a 0 angle to the normal, it should just head straight out 5. But as I make the angle bigger, this angle here, it changes. There must be some angle here, I, that makes it just come out here at 90. Yeah, the critical angle. So anyways, basically he's asking you to find this angle here that lets the light not really escape, that just kind of runs along the boundary, so to speak. So we know I, well no, we want I, we know or. So what's law now? Snell's law. It's sine I over sine or. But what's sine or here? 90, yeah. Now be very careful, people. In my last example of the refractive index, I did, what did I do? Sorry, air to water, air to glass. I should have really done glass to air, but I don't know if he actually said that in the question, did he? No. So if I'm doing glass to air, I shouldn't use 1.5. Instead, I should use the reciprocal, yeah, 1 over 1.5. Okay? If you didn't know that, if you go from air to glass or A to B, and then you change it from B to A, the only difference is the refractive index inverts, yeah. So somebody please tell me what the I is here. What is it? So sine inverse 2 over 3 basically. Now make sure it's in degrees mode now. Yeah.
Sine is
41.8.
41, so 42 then about, yeah? Okay. How many marks now? 1, 2, 3, 4, 5, 6, 7, 8. Okay, next one, 4 marks. This one's actually nice. This is your light, and it hits a diffraction grating with 800 lines per millimeter. Calculate the third order. So what you have here, look, there's your grate with your lines. The light wave comes in, and then you know what happens on the screen? You get your dots. So in the middle is n equals 0, and which one does he want? Yeah, so he wants n equals 3. What else do we need to know? We should know the wavelength of the light. Now what does he give us? Does he give us the frequency? 8.57 times 10 to the 14. Okay, so how do you change frequency to wavelength?
C equals
Well, sorry, can you read out the frequency? What was it?
8.57.
Omar, you have it in front of you. 8.57 times.
C equals
C equals
F.
F lambda. So C equals F lambda. So C over F equals lambda. So lambda equals C over F. What's that, please?
3.5.
What is it?
3.5 times
Times 10.
minus 7.
Now, we also need to know the distance between each grate here. He says there's 800 lines per millimeter. So that's per millimeter.
The distance between
So we want the distance between each of these little lines. So again, we've seen this before. Look, hey, look. If it's 800 per millimeter, that means it's 800 per 0.001 meters. 800 per that. Now you want 1 meter, right? No, sorry. You want 1 line, not 800 lines. So basically just divide this number by 800.
1.25 times 10 by minus 6.
What is it?
1.25
Yeah.
times 10 by minus 6.
Is that okay? Meters. So D equals 1.25 times 10 to the minus 6. So look, if I say something has 5 lines per meter, and I want to know how big it is between each line, then I just do 1 meter and divide it by 5. If I say it's 800 lines per 0.001 meter, and I want how much it is for 1 line, well then it's just 0.001 meter divided by 800. Okay? Now, it's in the formula book, but who remembers the formula here?
D sine.
What?
D sine theta.
Yeah, it's d sine theta equals n lambda. Isn't that it? Yeah. And he wants the
The
angle. He wants the theta. So I get theta equals sine inverse 3 times lambda divided by d, which is that. What's that, please?
$58.96.
59. Are we just on to D now, yeah? Photoelectric effect. That's nice. So you have this light and it hits a metal surface, and the maximum kinetic energy of the electron emitted from the metal surface is that. Determine the energy of the photon of light. So if you recall how this works, you have your metal and in comes some light. What was the wavelength of that light if you wrote it down? What was the wavelength? Dudes, come on, don't make me do all the work here.
3.57 times 10 to
Are you sure?
yeah. 3.57.
3.5 times 10 to the minus 7. And then what's the frequency? It's in the question.
8.56.
Yeah,
Yeah,
3.57.
times 10 to the 14.
That was 3 point... Dudes, right.
5.7.
I'm going to go with 5. I just wrote down 5 here, so maybe it was 5.7. I'm just going to write 5 for the moment, okay? And what was this frequency? Times
10 to the power
10 to the
14.
14.
hertz. Now that comes in here, and then what is released?
Photons, yeah.
Is it a photon or is it an electron?
Electron.
Electron. Electron is released. Yeah, and a photon is what went in. Okay, you are exactly right. The energy here is equal to, what's the energy? HF. And the first question is, what is the energy of the photon of light? So, no problem there. Energy equals HF, which equals, Planck is 6.67 times 10 to the minus 34, isn't it? And the F is 8.57 times 10 to the 14 hertz. So please tell me what that is.
5.68.
Go ahead, Brandon. Sorry, what's it?
5.68.
Yes.
10 by minus
10 by
minus 90.
joules. Now, that is the energy of the photon going in, and what should that equal? Well, firstly, that's part 1 done. Now part 2. Now, before I go on, that energy of the photon, what should that equal? What should it equal? The energy of the photon should equal the energy of the electron. Do you understand? So the energy going in has to equal the energy going out. Now, what is the energy of the electron here? It's the kinetic energy plus the work energy. This is the energy from its motion, and this is the energy required to release it, to free it. Like the ionization energy you've seen in chemistry. So, do we know this E here? We do. Do we know this? Well, it gives us... Oh, he gives us the kinetic energy. Yeah. So that's even easier than I thought, because he gives us the kinetic. What does he say it is? It's 1 times 10 to the minus 19 joules. And so we can work out this by a simple subtraction. We all know how to subtract, don't we? So it equals 4.68 times 10 to the minus 19 joules. Because this was 5.68 times 10 to the minus 19, just take that over to the other side. So minus one of these leaves me with this. Yeah? Really? 3 marks?
That's the work function? The work function for the surface is the energy released.
Yeah, that's what it is, yeah. Right. The last one here. What is the minimum frequency of radiation that will cause the photoelectron to emit from this metallic surface? What's the name of that?
Ionization.
No. Well, it's very close to it, yeah, but we have a special word for it in physics. What do you call the energy that's just about enough to release the electron? Oh, what's it called? The something energy. Oh, what is it called? The something energy. What is it? First letter? T.
Tell me transition.
No, it's not transition.
Threshold energy. Yes. So that's the energy you need just to release it. So what that means is there any kinetic energy? No, there's no kinetic energy because it just about is released. So here you get the energy of the photon must equal the work energy plus no kinetic energy. Well, that's actually not too bad, because he wants the frequency of the photon. So this is the thing we don't know. And do we know this?
Yeah.
We do. And what's the energy of the photon? HF. What's the work function energy? So the frequency will equal that divided by Planck's constant. Please tell me what that is.
6.6.
Planck is 6.67, isn't it? Times 10 to the minus 34.
So 7.06.
Oh, sorry, what is it? 6.63. Sorry, I wrote down 6.67 earlier. No big deal.
Minus 34.
What is it?
0.06.
What times?
And by 14.
So that is the minimum, that's the frequency required to just about release an electron from the surface. So if your photon of light has this frequency, it will just about free an electron from the surface, but the electron won't really have any velocity. Okay.